All right, so today, real quick here, we're going to take a look at the Chapter 4 test review session. Again, as we always do on or for tests and quizzes, I should say, we're going to try to prepare as best as we possibly can, kind of in this last-minute format, I suppose, in many regards. So, again, Chapter 4 test review, we're going to just be working through some problems that are very similar to those going to be seeing on the test. For those of us who were paying attention in class today, again, with that group activity that you guys are working on, a lot of these problems are going to seem pretty familiar in comparison to those. So, if you needed to, so to speak, read between the lines, I guess, it's probably some pretty good types of problems to know. Plus, you're given a Chapter 4 review packet. Again, always a good idea to know what's on as well. A lot of that same material. There's just so many ways that we can set that up. So, starting in with the graphing, I know that a lot of students seem to be, if there's a spot where you're maybe a little apprehensive, it seems to be on the graphing. Just a few notes to put up there. For this test, we want to be sure to know the graphs of the parent functions. Again, I know that that's something that I'll often refer to as, okay, well, what about the parent function for the sine curve or for the tangent curve or whatever it may be? Knowing what those are, that's going to be pretty significant. Also, knowing how to find A, B, C, and D from the given equation. Again, knowing what they represent. A is the coefficient in front of the trig value or trig function, excuse me. B is the coefficient in front of the variable, the x or the theta. C is the amount being subtracted from the x to the theta within the parentheses. D is the amount being added or subtracted on the outside. And then from there, of course, being able to get to amplitude, period, and starting point. Once we know how the amplitude, period, starting point work, I would absolutely encourage you to continue to use the framing method. I know that some of us, again, as I was watching the group activity today, some of us have kind of all ventured away from the framing method, and I was noticing a lot of students who had opted to do that. Again, maybe we're struggling a little bit more. So I wouldn't be as adamant as I am on this framing method if I didn't believe very, very completely that it's our best option. So something to consider. Also, we want you to be able to identify critical points and or asymptotes on the parent function. Meaning, critical points is that if we're drawing a sine curve, for instance, when we draw out for the period, we draw out one period in the frame, we're going to have 5 critical points, and being able to identify where those points are located is going to be important. The asymptotes, identifying where the asymptotes are located, but also being certain to just draw them on the graph. That's another spot where some students have struggled previously. So, if we're to take a look at this first problem, we want to go ahead and graph this. F of x is equal to negative 3 sine of 2x plus pi plus 1. It's down just a little bit. So, in order to start this problem, I would encourage you to consider A, B, C, and D. So, for this particular problem, as we can see, A is negative 3, B is 2, C is going to be negative pi. Remember, it's the amount being subtracted from the x, so that's technically, even though it doesn't look like it, that's 2x minus negative pi, and then D is 1. So how this is going to translate for us, remember that amplitude is the absolute value of A, so in this particular case, the absolute value of negative 3 is 3. The period we calculate, as long as it's sine, cosine, secant, or cosecant, we're going to calculate by taking 2 pi divided by B. So in this problem, 2 pi divided by 2 tells us that our period will simply be pi. And then finally, our starting point. The way we calculate the starting point, it's always C over B, comma, D. So when we attack this, C is negative pi over B, which is 2, comma, D, which is 1. Now we have our amplitude period starting point. The other piece that we always typically make note of is whether or not there is a reflection. Because I'm noticing that A is negative, that tells us that there absolutely will be an x-axis reflection taking place. So what that means for us is that we want to think about the parent function and, I guess that needs to be inverted. So we'll get to that in due time. For this particular problem, looks like I let each box be equivalent to 1/4 pi, excuse me. So pi over 4, so meaning pi over 4, pi over 2, pi over negative pi over 4, negative pi over 2, pi over 4, pi over 2, 3 pi over 4, and pi. I'm going to try to mark these to where it's somewhat out of the way. So we get pi over 4, pi over 2, we've got 3 pi over 4, we have pi going 0 in the negative direction, negative pi over 4, negative pi over 2, negative 3 pi over 4. And again, even that last line would be negative pi. We're going to go that far. So where we want to begin, of course, is at the starting point, excuse me, which is at negative pi over 2 comma 1. So there is my starting point. Next up is the verticality here. So I need to, from the starting point, I need to move up the amplitude, which in this case is 3, down the amplitude, which in this case is also 3. Now I need to move over the period. So we said that the period is pi, so that means that I need to move over an amount of pi. So if I were to move over pi units, that's what it's going to look like. All right, so this is my outer frame. Once we have the outer frame, we want to go to work on what's taking place in the interior. So we always need to start with the 0 line. Again, we're going to cut through, horizontal line through the starting point. Now I need to cut into fourths vertically, so typically it's easiest to cut it in half and then cut each of the halves in half. So once we have this partitioned out, now we're ready to get to work. So remembering that this was a sine curve, we're going to consider that y is equal to sine x. Again, the parent function here for the sine curve, it goes through the origin up then down, looking like that. So since the parent function goes through the origin, we should absolutely expect that the sine curve is going to go through the starting point. The other thing that's important is that it normally moves up as we go to the right, but since there is a reflection taking place, we're going to move down as we go to the right, and it's going to cycle back through to give me one full period, looking something like that. So if our job, again, was to go a little bit further and to identify these critical points or these key points, we hopefully would be able to do that with relative ease. Looks like this first one, again, my starting point was at negative pi over 2 comma 1. Second down here, this is at negative pi over 4 comma negative 2. Third, in the interior, I don't know the best place to put this. We'll just call it 0 comma 1. Up top, we are located at pi over 4 comma 4. And lastly, we're located at pi over 2 comma 1. So identifying those points, we said that it's going to be important to identify asymptotes on a sine curve or cosine for that matter. There will not be asymptotes. Not. All right, so the next problem we want to take a look at here is sketching the right triangle corresponding to the trig function. Then it says to find the third side and the other 5 trig functions if we know that the cosine of theta is 9/15. So this is the type of problem that we don't really have to put it into a coordinate plane. So instead, we just need to draw a triangle, marking out an angle for theta. So if we were to allow this to be theta, cosine adjacent over hypotenuse is going to follow suit. So we're supposed to figure out the other trig functions, meaning that we want to figure out the sine of theta. We already know that the cosine of theta, again, is 9/15. The tangent of theta, we want to go with the reciprocal pairs as well. So the cosecant of theta, the secant of theta, and the cotangent of theta. This is now the goal is to figure these out. Now, even though we're given that the cosine is 9/15, hopefully the first thing that we're realizing is that, yeah, that's actually going to reduce now. That's going to divide it 3 at the top and bottom. We're going to call that actually 3/5. Once we know that that's 3/5, the reciprocal secant is going to be 5/3. In order to figure out the sine, cosecant, tangent, or cotangent, we're going to need to know that opposite side. So in attacking the opposite side, which we'll call x for right now, we've got to do the Pythagorean theorem. We'll call this x squared plus 9 squared is equal to 15 squared. X squared plus 81 is equal to 225. Excuse me. So when I subtract over, we're going to get that x squared is equal to 144, square rooting both sides. We know that value cannot be negative, so we're going to stick with the fact that x is equal to 12. All right. So once we know that that opposite side is 12, we are now in business. The sine is simply going to be the opposite over the hypotenuse. We'll call that 12 over 15. hypotenuse to 4 fifths, which again, cosecant is now going to be 5 fourths. For the tangent, the opposite over the adjacent, the opposite again is 12 over the adjacent, which is 9, but that's going to clean up to 4 thirds, and the cotangent then is going to clean up to 8 thirds. All right, so again, simplifying is always very important. If we see radicals, we have to simplify those. Fractions, we have to reduce those down as well. All right, second problem here, or next problem, I should say. I think the numbering got a little off with where I put that graph. We want to find the exact value of secant, if the tangent of theta is equal to 12 fifths and the sine of theta is less than 0. So this problem now, the placement matters. Again, we've got to make sure that we put this in the correct location. Now the key here is to start with the fact that the tangent of theta is 12 fifths. For the moment, I don't care that it's 12 fifths. I just care that it's positive. So if we're considering that the tangent is positive, remembering that we've got that little trick of all students take classes working our way around, where it means that all three, sine, cosine, tangent, are all positive in the first quadrant, the sine is positive in the second quadrant, the tangent is positive in the third, and the cosine is positive in the fourth. And the reason for this is that the cosine, that represents your x term, your horizontal allotment there. So if we're moving in the positive direction, cosine is positive, that means that we've moved to the right of the origin. The sine is simply going to be your y term, or your vertical component. So if the sine is positive, you have to be above the origin, meaning that we have to be in quadrants 1 or 2. If sine is negative, you're below the origin, we have to be in quadrants 2, 4, or 3 or 4, excuse me. So as we are getting back to this, the tangent we know is positive, as we can see here. Tangent's going to be positive in either 1 or 3. So we know that we're going to be in quadrant 1 or in quadrant 3. It goes on to tell us that the sine of theta is less than 0. That means that the sine is negative. So that means that the sine is negative, implies that we're going to be located below the origin, so in quadrant 3 or in quadrant 4. So quadrant 3, quadrant 4. So right now we're looking for the overlap. The first piece could happen in 1 or 3. The second piece could happen in 3 or 4. They overlap in quadrant 3. So that means that I need to draw my sketch. I need to draw my triangle so it is located in quadrant 3. So I'm going to draw something looking roughly like this. My right triangle, there's theta. And we're supposed to draw this to where the tangent is 12 fifths. So the opposite over the adjacent is 12 fifths. But since we're in the third quadrant, that means that if I move to the left 5, that's negative 5. If I move down 12, that's negative 12. Luckily, tangent is the opposite over the adjacent, or in this case, the sine over the cosine, and the negative 12 over the negative 5 still cleans up to be 12 fifths with those negatives canceling out. So where we need to go from here, if our objective is to figure out the secant of theta, we know that the secant of theta, it's just simply the reciprocal of the cosine. Cosine's adjacent over hypotenuse. That tells us that we're looking for the hypotenuse over the adjacent. Great, but I need to figure out what the hypotenuse is. So as we come back over here, we're looking at negative 5 squared plus negative 12 squared is equal to that hypotenuse squared. Again, I'll ruin the suspense. We're going to clean this up to get that x is equal to 13. So once we know that the hypotenuse, which by the way, the hypotenuse will always be positive, no way that can be negative. So once we get that the hypotenuse is positive 13, like I said, this here, now it's just a matter of plugging in. So the secant of theta is going to be equal to the hypotenuse, which is 13, over the adjacent, which is negative 5. So for me, I just like to bring that negative out front, or even into the numerator. Negative 13 fifths is what we're looking at. All right. Next problem. It's very similar. It's the same thought process, but again, actually asking you to do less work. So again, using all students take classes as another kind of benchmark here. If we're told that the cosecant of theta is less than 0, that means that the cosecant is negative, which means that the sine is negative. Below the origin, we're in quadrant 3, or we are in quadrant 4. If the tangent is greater than 0, that means the tangent is positive, which is taking place in quadrant 1 or in quadrant 3. Quadrant 1 or quadrant 3. So we're looking for the overlap, which, as we look again a little bit closer, looks like quadrant 3 is going to be the winner there. All right. So I'm going to stop the podcast here. I'll have you pick it up here in the second